I'm going to start class by talking briefly how we find the course. So I sent you a link here in our Google Classroom. I'm pretty sure I sent it via Google Classroom. If I didn't, I will resend it. But my course has an ID associated with it, which if you should search the ID, you should be able to find it. Okay, let's see. Sorry, it's kind of hard for me to see. Tiny little screen. Okay. Okay, this course ID right there, the J dog or whatever, right here on the CHE in our Google Classroom. You should be able to, when you go to here, if you don't have a course, you could search for a course. And if you use the course ID, that should be able to pull this up. Now, I already have some people registered, and those registries have, I think, as they're just saying, about a 2-week trial period where until you get the access cards from the bookstore, you can still access all the homework and all the assignments for 2 weeks. The idea being, say you change your mind, like, oh, this is not, I'm in the wrong chem course. You can drop out without having paid any money, but due to our Barnes & Noble bookstore, it's not an issue. But either way, so that Google ID, that course ID is up on, and that course ID is up on the Google Classroom, and so we should be able to use that to gain access. Okay, so I already have like 6 or 8 people enrolled, but no one has the cards yet. The cards are coming. I've been told they should be here, what, like end of the week or something like that. But you know, we lost a week when we started a week early, so hopefully they'll be in early next week. The bookstore should contact me as soon as they get them. As I said, we have it's the 14th. If another week goes by, everyone still should have access. So no one's going to be kicked out before the first assignment. So we'll worry about that in a little bit. Okay. So let's get back to where we were in the PowerPoint. Oh, I need to minimize it. Okay. So we last finished off talking about the rules of recognizing significant figures, significant digits. Remember, these are numbers we can reliably report without worrying about inaccuracy. We could report as many numbers as we want, but at some point, the standard deviation in what we actually have overwhelms the number. So if I said, for example, real quick, if I said I have 102 plus or minus 5, how much can we reliably say we have? Well, we can't say we have 102 because the uncertainty is far greater than the 2. Plus or minus 5. I could have 107. I could have 97. Either of those numbers are equally likely. So when it comes to certainty, I know this digit and I know this digit, but I do not know that digit. That digit is a big question mark for me. So what we're saying is, if I had 97, what would that round to? It would round to 100. If I had 107, that number, what would that round to? 110. The idea with uncertainty is you're within plus or minus 1 of the last significant figure. If you round up 1 or round down 1, you won't be really changing your number. But the non-significant figure could vary incredibly wildly depending on where we're at. So that's what I mean when I mean it's a significant figure. We know these two numbers. It's around 100. I do not know this digit. This is my question mark. This is my unknown. This is my X. That's what it means to be significant. So going back, we said if there is no decimal point, we take the last non-zero number, last non-zero number, and every digit to the left of it is considered significant. So in this case, without this little thing here, if I just gave you 102, we would know all these guys are significant. But we're not right into standard deviation yet, and we're not going to really worry about that during our general chemistry too much. Now, if there is a decimal, then we take the first non-zero number, and every number to the right of it is considered significant. I mean, I got to clear my throat. Yeah, okay. So now, but keep in mind, in the second example, 0.010, the 1 and the last 0 are significant. But we run into something very interesting when we have decimals like that. Let's take a hypothetical example right here. Let's say 0.00206, just as this example. 206. So those, I take the 2, and every number after that 2 is significant. So the 206 is significant. Those first 3 zeros just tell us it is a small number. But note, I stopped at the 6. I can't go any farther. I can't go any more decimal places. Any number after the 6 would be my uncertainty. I couldn't say 2063. I couldn't say 2067. I don't know what comes after the 6. It is an unknown. So these are just insignificant numbers that tell us it's small, but I have to stop here. And so it is enclosed by 2 regions. So this is where we start. This is where we have to stop. We can't go any further without making up numbers that aren't necessarily true. So now, just a quick reminder, as we record things in the lab, we are going to want to record, if it's on a digital scale, we're going to want to record as many numbers as we can, and we'll see why in the next couple slides. But if a balance reads 5.320, we want to record all of that number. We don't want to write 5.32. Why? 1, 2, 3, 4 significant digits. 1, 2, 3 significant digits. We have lost a significant digit. If the number instead read 5.000 and I write down 5, I've written down 1 significant digit instead of 4 significant digits. And one thing last to remind you, when we measure something, how do we know when to stop measuring? We always stop measuring 1 unit past the last marking. This example I gave in Tuesday, Thursday class. Like take a graduated cylinder. So 1, 2, 3, 4, 5, 6, 7, 9, 10. 1, 2, 3, 4, 5. If I had this and I have a liquid filled up to here, we will measure the bottom of what's called the meniscus, the bottom of the liquid bubble. And what can you say? That's 1, 2, 3, 4, 5, 6, 9, 10, 11, yada, yada, yada. What can we say about that? That is between the 8 mark and the 9 mark. The markings only go up to the 1's place. So for 100% certain, if you are reading this right, without a doubt, you will say it's 8 something. You will not disagree with your partner. Everyone will say it's 8 something. You won't say it's 9. You will say it's 8, but you can say something more. It is not just 8, it's 8 and a bit. And now here's where it gets a little tricky with uncertainty. You are going to use your best eyesight to measure how far is that. Is that exactly in the middle? Is this a little below the middle? A little above the middle? Maybe you want to say that it's 8.4. And that's as far as you can record. The beauty of this with measurement is that it allows for some discretion from you to you to you. Your partner may say that's 8.5 and disagree. But the idea is it's 8.4 plus or minus, say, 0.2. So you could range within 2 units of each other and still be accurate. You can range within 2 units of each other and still be accurate because maybe your eyesight's a little bit better, maybe theirs is a little bit better. But the idea is, if you say it's 8.4 and they say it's 8.5, it's fine because remember, we're allowed to round by 1 or 2 units and still be accurate. But there's no way in hell you can say, oh, that's 8.432. How the hell did you manage to figure that out? I know I'm not like, I don't know if you're watching Amazon Prime Hannah, where I'm like genetically engineered with like wolf blood, where I can like see this and so be so accurate that I know down to 3 decimal places. I know I'm not. I don't think many of you are. So we're only reporting what we can rely on. And so we always record between the 2 markings if you're measuring a mark. So you're always going 1 more decimal place past the marking if it's a graduated case. And that way you can keep as many significant digits as possible. If you just said 8, well, then you have 1 sig fig. But if you say 8.4, you at least have 2 sig figs. And we'll see why that's important in the next 2 slides. Well, okay, moving on to the next slide finally, because I just wanted to make sure we're on the same point before we jump ahead. So practice. What are the sig figs here? And turn these guys into scientific notation. So we got to look at what we have and what are the rules. So the first number, 34050 degrees C. So, yeah. And we look at that. what is the first thing we should note? We should note, as is reported, there is no decimal. No decimal. So that means we use the no decimal rules. It is a big number with no decimal, means we take the last non-zero number and everything to the left gets counted. So that means we should have 4 sig figs. Now, as we put this into scientific notation, remember, greater than 1, less than 10, 3.405, we would have had to move 1, 2, 3, 4, 5. So, would say 3.405 times 10 to the 5th Celsius. So we keep only the significant figures or the significant digits while we turn this into scientific notation. The next one, 0.004590. 4590. One thing you should immediately note, a decimal, which changes the rules. Decimal means we take the first non-zero number and everything to the right. So once again, we have 4 sig figs, 4 digits. And when we move this over, 1, 2, 3, so we have 4.590 times 10 to the negative third. And that's grams. So that would be, as we'll learn in dimensional analysis in a bit, that would be something like, well, there's 4.590 milligrams. The last one, 3.04. So it has a decimal. So the rules is first non-zero number, everything to the right. So in this case, every single digit reported is considered significant. Every single digit is significant. So all 3. Now, if we were to turn this into scientific notation, you would say that's 3.04 times 10 to the 0th power. You wouldn't really want to turn this into scientific notation, but if you had to, 10 to the 0th. The rule of math says any number raised to the 0 is 1. Any number raised to the 0th power is equal to 1. And any number multiplied by 1 is itself. So what we're saying is 3.04 times 1 is 3.04, and that comes back out with our initial value. As I said, would you really want to turn that into scientific notation? No, it's not worth your time. But if there was a silly question that asked for that, you could. But the first thing we need to be able to do is recognize this. Now, why are we bothering to learn this stuff? Because when we do calculations, we are going to be losing significant figures. And the rules for multiplication and division, addition and subtraction, will change how they lose them. But the basic idea here, to add uncertainty into certainty, you lose your knowledge of a number. If you add an unknown to a known, the known loses its clarity. We no longer know what the result is. So we have rules for addition and subtraction. It's one way. Multiplication, division, it's another way. Now, some of these guys you could memorize these rules, but it comes with practice. we look at the learning curve assignment for significant digits, there's lots of good practice in that you can use. Get this down. But okay, addition and subtraction, we lose position or location of the sig fig. We don't lose the number of sig figs, we lose the position of the sig figs. So how do we do this? We set this up vertically, like grade school. We set this up and down, and look, where is the last position of the last sig fig? So if I do 3.40 and add that to 0.5, 0.054, add these together, put them right over top of each other. You should note one thing. 3.40, what did I say? After that 0 is the unknown, is the big question mark. And it keeps going out question marks. After 0.054, after the 4, we have a question mark. Keeps going out. So that question mark is our uncertainty. We don't know what that number actually is. So we're going to draw a line right there. 3.40, don't know. 0.054. You do the math. You can punch this into your calculator just fine. The calculator tells you 3.54 is your 454 is your answer. But that 4 is on the other side of the line. That 4 is a 4 plus a question mark. That question mark could be anywhere from plus or minus 4. And because it could be anywhere plus or minus 4 or even 5, we don't really know what this digit is anymore. So all we can say is we know this is 3.45. That's all we know. So, because what happens if this is negative 4? This is negative 4. This goes down to 0. And we have 3.45. What if this is positive 4? You have 3.458. That can round up to 3.46. The idea being, our answer is somewhere between 3.45 and 3.46. And I know it's between there, but I don't know any more accurately than that. I know this is tricky. I know this is not the most fun math because it's very weird and obtruse. And so it's just something we got to kind of practice. You got to practice. So what you want to do is line these guys up. Line these guys up. Find out where the last sig digit is. And then round past there. So in this case, 400 without a decimal point, this guy is right here. 400 without a decimal point, it's right there. 342 without a decimal point is right here. So when we subtract these two, 400 minus 342, oh, sorry, my bad. Is it 42? Jeez, 4,200. 4,200. That changes everything. I'm going from the slide, people. Someone shout me out. Someone yell at me when I get that way off. But 4,200 minus 342. You can do the math. You can round later. But the idea here is, so that's going to be 3,858. Now, because of that, the 5 and the 8 are past the line. So what do? We're going to round up or round down depending on where it is. Since this is above 5, we're going to round up. That doesn't invalidate my 42. All it says is that I can only tell you that I know we have around 3,900. I can only tell you I have 3,900. Say I have a stadium that holds at max capacity 50,000 fans, and it's filled to capacity. And then you, I don't know, say like, I don't know, there's a protest on field, and like 1,000 fans leave. We don't know exactly how many, but we know we lost some portion. Can you reportedly say how many fans we lost, or can we only really report a fraction? We can say, well, we lost about 1,000 fans. We don't know if it's 1,110. We weren't counting them all when they left. They just stormed out. I mean, you can't always report everything accurately, but you can give an approximate amount with some reliability. And the important thing is we're trying to report what we can reliably give. And the calculator will give you everything, will give you all the digits, but it doesn't know what's considered reliable or not, unless you're using the scientific figures thing in the Sci tools. So I can show you how to get to that if you have a graphing calculator. So feel free to use that until you get more used to it. Now, multiplication and division are a little bit easier in a way, but still a little bit harder. Where when you do these, instead of caring about the places in your multiplication and division, you care about the sheer number of significant figures. So the more sig figs a number has, the more sig figs you can keep. I could mathematically try to show you why this is the case, why this rounds up or rounds down. I don't want to. It's a pain. Just note that the number of sig figs you keep will change how accurately you and how reproducibly you get the same numbers. So the example I give here is 45. Say you're measuring a room. You say 45.0 meters, 1,004 meters, and 3.0 meters. So 45.0, that's 3 sig figs, times 1,004, that's 4 sig figs, times 3.0. That's 2 sig figs. You punch this into your calculator, you got 1,35540 meters cubed. But because we used 2 sig fig number, we can only reliably report the first 2 sig figs. So that means we can only report those 2 digits. So 1,35540 rounds up to 140,000. That's all we can report because we have 2 sig fig digit. Now, taking the exact same number, if I instead said 3.00, suddenly we have a 3 sig fig number. I take that same exact result, and I could now reliably say this would be 136,000. Now, why is this important to you, to me? Well, when we're doing our calculations in lab, we are going to be doing a lot of multiplication and division. Say you're finding out density in like a week or two. You're finding out density of some metal. You're going to take a mass that you weigh, and then you divide by a volume that you measure. If you know that volume accurately to say 4 decimal places, and you know that mass to 4 significant figures, your answer will be accurate to 4 significant figures. But say you weigh this out and say instead of this being 25 grams, you weigh it out to 25 instead of being 25 grams. So that's 5 sig figs. You weighed out to be 25.0. Now suddenly the number when you divide will not be 4 sig figs. It will be 3. Say you only wrote down 25. Now your number will only be accurate to 2 places. And so the idea in lab, record things as accurately as we can to the most number of sig digits. So when we do our math, our answers are either going to be 4 decimal places or 3 decimal places. And that's a big thing to keep in mind. When we do our math, we are going to try to keep things to either 4 decimal places or 3 decimal, like 4 sig figs or 3 sig figs, depending on how accurately we know a given number in the lab. But the idea here is you do a crappy recording of one measurement. That's going to throw off every measurement down the road because you lost a digit here, you're not going to get it back later. That's my warning to you guys. That you lose a digit at the beginning because you didn't measure something worth a damn. Later down the way, you're going to have just numbers. Oh, it's accurate to 1 decimal place instead of it's accurate to 3. And that's the idea here. We record things as accurately as we can so that when we report things, you know, this is what we got. This is what we got. And I'm not giving anyone a load of bullshit. Okay, so we'll finish off sig figs with this practice problem. So, and then we'll move on to something I swear will be easier. Dimensional analysis. I know that sounds complicated, but it's way, way easier if you can learn to set these guys up. So significant figures. So 4.43, we add on to 3.294. Do that. And we want to, so note, I put them over top of each other, hopefully so the decimals line up. I want the decimals to line up. And so at this point, I'm going to put a line where the last digit is. 1, 2, tens, hundreds. So when I do this, feel free to do the whole math in your calculator. Just remember, as you do the whole math, you have to round in the end. So 7.724 rounds to 7.72 grams. And just because I'm doing this in my head or cheating one way or another doesn't mean you have to do anything in your head. That's what our calculator's for. Next one, we have 3.25 grams in 1 mil, grams per mil. We're multiplying by 0.035 mils. 0.035 mils. So I look here, I say 1, 2, 3 sig figs. 1, 2 sig figs. So regardless of what my answer gives me, I want to round to 2 sig figs. Now, I'm not going to try to do multiplication in my head just because it's going to waste time. But you do this, you get an answer that reads 0.11375 grams. Your calculator will spit the whole thing out. It doesn't know any better. It looks at pure numbers, not applied numbers. It doesn't understand what it means to be significant. So either way, these two are right out. But between 2 and 3, we go 2 sig figs, we keep the lower number. So I'm going to round to 0.11 grams. It's not saying there are not numbers here. It's just saying I cannot reliably say what those numbers are. All I know is that it's somewhere close to 0.11. I cannot say with any more certainty that it's any more than 0.11. The last one, it's a hard one because it's two-parter. It's taking addition and subtraction and then adds in multiplication division. 3504 minus 31.4 is the first step. So we want to do this systematically. So we draw this. So in this case, we lost a sig fig from in front as well. Sorry, not 4. 3.64. Now here's the interesting thing. You can round it now or you can round later as long as you keep in mind what is the sig fig now. What is the sig fig now? So note here, my number should be 3.6. So that is two significant figures. When I divide by 1.404, I have to keep in mind I have two significant figures. Sometimes it doesn't matter which order you round in. Sometimes it'll change your number by 1 unit. That's never usually an issue. But so I take the 3.6, I divide by 1.404, and I will get my answer. So 3.16. I can click the next slide. And you get you get a whole spew, but 2.56 rounds up to 2.6. So your answer is, with some reliability, 2.6. If I'd gone 2.5, that still would have been acceptable. What? You would have the units of grams per milliliter. And we'll talk about that in just a second because that's our next topic. Dimensional analysis. Okay, so dimensional analysis. What is this? Dimensional analysis is how do we transform one unit to the other. It is the bread and butter of all the math. Once we move past significant figures will be a small part of your class. It will mainly show up in lab. Dimensional analysis will stay with you the entire time. So if significant figures is kicking your ass right now, please note, it will not be a crippling point. If you still don't understand it in 2-3 weeks' time, it will maybe burn you a bit on test 1, but it's not going to keep coming back on test 2 or test 3 or test 4. It will kind of ping you a bit in lab, but it's not going to be something that's going to keep you from passing the lab. If you do not know how to do dimensional analysis, come see me, come chat with me. We need to work this out because dimensional analysis is how we get through everything going forward mathematically. So dimensional analysis is how we transform units. It uses a relationships, though, that we're going to multiply units together or divide by units together the same way as you would multiply and divide numbers. So remember how when you multiply 10 to the x times 10 to the y, we can say that is 10 to the x plus y. Well, the same thing with units. Same thing with units. If I have grams to the first and I multiply it by grams to the first, the result will be grams to the second, or grams squared. If I have grams to the first and I divide by a number that's grams to the first, I will have grams to the 0th, which is 1. They have canceled out. So as we go through our math, units will either combine or cancel out to get us to where we need to be. More often than not, we will worry about canceling out units. But just an example of combining units that you've seen. You've seen this in math class if you've had any math class at all. Because you say, what is the area of this room? If this room is 10 meters by 20 meters, 10 meters by 20 meters, how would you do that math? Well, you'd say 10m times 20m, and say 10 times 20 is 200. But we didn't really care about the units before. But m times m would be m squared. What is m squared definitive of? A unit of area. By multiplying the length as a distance and the width in a distance, we get the derived unit area for that system. When we use density to calculate this, calculate density from a mass and a volume. Density, by definition, is mass over volume. Density is mass over volume. But calculating this, we're saying if I have a 50 gram mass, we can always say any given number is over 1. Because 5 divided by 1 is 5. When I divide it by the volume, 1 over 1.85 milliliters. Well, the numbers divide just fine. The numbers divide just fine. You get 2.7. But the units do not divide because grams are different from milliliters. So what do we get? Grams over milliliters is our final result. But what is grams over milliliters? It is the derived unit for density. So if you do the derived unit, you get the derived unit of density because grams and milliliters are incapable of canceling each other out. Now, where we're going to use this more often than not is in conversions. And this will help you by setting these guys up. My Corgi, who's a chunker, weighs 34 pounds. If I wanted to know how many kilograms that is, I can set this 34 pounds over 1. And in every 1 pound, we have 0.454 kilograms. So note, I set this up pounds on bottom, kilograms on top. Why? It's the same way is there's a pound here. We'll cancel with a pound here. And that leaves us with the answer of, you do the math, 34.454 is equal to 15. And since kilograms is the only unit left, 15 kilograms. I know I need to multiply by 0.454 and not divide by 0.454 because of how the units would cancel. If I did this the other way around, if I said 34 pounds and I did this pounds on top, kilograms on bottom, I would get pounds squared per kilogram. And that is a unit that makes no sense. We have no way of conceptualizing that. That has no meaning for us. So we can always watch, if we do the dimensional analysis right, the unit we want gone gets gone. The unit we are striving to get ends up in our answer. So we're always going to cancel out units. Always going to cancel out units as we move across to the answer. This is the same concept. What is 12? 12 is a factor of 3 times 4. If I is equal to 3 times 4. If I said 12 divided by 3, what can we say? Well, if this is 3 times 4, the 3's cancel. The answer is 4. Because 12 is a factor of 3 and 4, we can simplify this and say any number divided by itself cancels out. Any number divided by itself. Here's a harder but easier one. 110 is equal to 55 times 2. So if I take 110 divided by 2, the 55 stays, the 2 is removed, and we're left with 55. You can do the math, but the idea is that and 55 is in fact a factor of 5 is equal to 5 times 11. And so we can do this in many different ways. The same way as we're canceling units. We're always canceling units as we go across. So I will look at this last slide, and that's where we're going to finish up, just because that will put us at the exact same spot as my Tuesday, Thursday class. But we'll probably reiterate this guy on Monday. So how will we solve these problems? There's essentially a way we can go about this that is pretty reliable. Yes, if you're good, you can skip some of these steps. With practice, it will become a lot easier. But if your math is not up as good as you would like it to do, taking these steps will help you. So step 1 is always determine what we're looking for. So read the question carefully. Determine what is given, what we're looking for. Trying to figure out where's our starting point and where's our ending point. Step 2, determine what relationships we can use. What conversions can we use to leapfrog from where we're going to where we want to be? So, for example, if I have a mass of water and I want to know what is that water's volume, a relationship I could use is the density of water. If I have so many feet and I want to know how many meters there are, I could either find the feet to, or I could go feet to inches, and then inches to centimeters, and centimeters to meters, depending on which guys are more readily available to you and more convenient to use. But those are the conversions that I can use to jump from feet to meters. Now, this one's a big one. I really say you should do this a lot until you get really good, and even then you should still do this. Set up the problem. Actually put it down, set it up, and show all your work. Put it on paper, show all the units before you solve. Because if you have a problem and you go like, oh, why is this wrong? And I have no work and you just punched it in a calculator and hit enter, I have no clue where you went wrong. If I see the work, I can see, oh, you did this. Oh, check how you typed it in your calculator. I can see this is a common tripping point. You have all the work right. It must be a calculator error. But without any work, it's my best guess. So, but if you put the work down, I can immediately see where an error might have occurred. Then final thing, this is the thing that most people skip, and that's fine. But check your answer. Check your answer. Does this sound reasonable? Is this a reasonable sounding result? Does the magnitude sound right? If I divided a big number by a big number, did I get a larger number? That's a dead giveaway. If I said the amount of like inches in a mile, and then I divided by the number of miles it takes to get to the Empire State Building from here, and I got a I'm trying to figure out how I would do that, but maybe the other way around. If I got a number that was way too, like if I got a number that's way out of scale, it's like it got bigger when it should have gotten smaller. You might be able to tell right away. And even when I just punch it in again, double checking your results, sometimes a good thing. I've seen people all the right work and they just made a typo in their calculator. If they didn't check it, it's like, oh, why did I get it wrong? It's like, oh, you just typed that in wrong. So checking it is nice if you have the time. I understand we don't always have the time. But that is where we're going to leave off. We are going to reiterate this again on Monday. And then we'll start going through some actual dimensional analysis problems and showing how to set up these problems and do them right. In the meantime, I'm your Professor Andrew Evans. I will see you guys next week.